All right, so in the last lecture I showed you that our course is going to look broadly like this here. The course EE210 Microelectronics 1. Again, this is causing a problem. All right, so the course EE210 is basically an analog circuits course, and within analog circuits we'll be mostly doing amplifiers, and initially we'll be looking at building blocks of amplifiers. Typical amplifier is a multi-stage amplifier, consists of different stages. So we'll be looking at those different stages which are there, and towards the end we'll put all of them together to make a operational amplifier. And but before we start talking about circuits, we have to understand the device out of which the circuits are built. And the devices include bipolar transistors and MOSFETs. Okay, and that's why we need to understand. We need to begin with device models. All right. So 3 questions that you should keep in mind. This course is a circuits course, so our interest is in circuits. The issue does arise. Circuits are made of devices. The issue does arise. To what extent do I need to understand devices? If devices are needed for making circuits, a question may naturally arise in your mind. Shouldn't a device course be given first and then a circuits course come second? A device course is a 311 course and circuits course is a EE210 course. But we'll see the device, the knowledge of device that we need is basically, for us, device is a black box. And what we need to understand is the terminal characteristics of the device. 311 is a course where we go inside the device and we try to understand why a device behaves like that. For this particular course, all we need to understand is the terminal from the outside. How does a device behave? For example, a bipolar transistor or a MOSFET, from an outside, if I apply this voltage, this current will flow, right? So we need to understand what the behavior is. Why the behavior is like that is not the topic of this particular course. Why current, let's say, increases quadratically with voltage in a MOSFET is not the topic of this course. The fact that it increases quadratically with voltage is important for us. Okay? So we need to understand devices, but from a circuit designer's perspective. Anyway, so that's one question that is there. The other one, question that you will see is important. How is an inaccurate model useful when accurate models are available? Okay, keep that in mind. All of you have heard of this small signal model, right? So an issue does arise. How small is small? Okay, when can I use a small signal model? All right, so let's begin with the necessity for models. Now, if our interest is in circuits, our interest is in analysis and design of circuits. So let's look at analysis. Now, analysis typically is what? Given any circuit, what you do is you transform it into a set of mathematical equations. And then, of course, you solve it to get the answer that you're looking for. Right? So here is a circuit. And how do I transform it into a set of mathematical equations? Well, I apply KVL, for example, to this particular circuit. If I apply KVL, I get Vs equal to the voltage drop here plus the voltage drop here, right? So I apply circuit laws, KCL and KVL, to get some equations that you see here. But that's not the complete story. I need more equations to solve this. And where do the other equations come from? Basically the model of a diode, right? So the IV model of a diode. That's the other equation that comes in. And so KVL and KCL will give me one set of equations. And the other set of equations will come from the model of the diode that is there here. And the model of a diode, one model of a diode is an exponential diode model, which says the current is exponentially related to diode voltage here, right? So there are 2 sources of equations that you see here. One source is application of circuit laws, KVL and KCL. Now, have we used KCL here? Well, it's so simple that you don't see it, but I have used a KCL, the fact that the current here and the current here are the same. Right? So at this particular node, it's trivial, but at this particular node, I've applied KCL to show that the 2 currents are equal. And note that I've already used a model. If I were to write this purely on the basis of KVL and KCL, I would have written as Vs equal to VR plus the VD. That's what my KVL would have given me. Then I've used a model of a resistor. What is the model of a resistor? V equal to IR. So I've already substituted the model of a resistor here. And then I have to use a model of a diode. So basically, analysis, as you can see here, is transformation of a circuit into a set of equations. Where do these equations come from? They come from application of KVL and KCL. That's one source. And the other source is the model of each one of the elements. So it shows you that I cannot analyze circuit unless I have a model. I can't proceed. If I didn't have a model of a diode, I couldn't have analyzed this particular circuit. So models are essential. They are the prerequisite to solving any particular circuit. All right. Now note, what you are seeing here is that a circuit is being transformed into a set of mathematical equations. The reverse is also true. I can take a set of mathematical equations that you have and transform it into a circuit. Obviously, not all mathematical equations can be transformed into a circuit, right? But the reverse process is also true, which we may see sometime later on. All right, so this is an example from a diode. Similarly, all circuit analysis examples will have the same thing. Suppose I'm interested in knowing what is Vout in a MOSFET. One set of equations come from KVL, from that. The other set of equations will come from the model of the MOSFET here. So I need a model of the MOSFET to proceed and analyze this particular circuit. So VGS is given here, is 1.2. KVL here gives me Vout equal to VDD minus IDS RDS, and the rest of the equations will have to come from the model. So we know that models are required, models are necessary. So what is a model? Right? We know what it is. What is a model? The definition that I like is the ones that are highlighted are important. A model is, first of all, a representation. It's not a real thing. It's a representation. And for us, the representation is mathematical in nature. It's not a physical model, something that, 3D model, something that you can touch and all that. It's a mathematical model that we are talking about. So it's a representation. And the other important point is, a model is always built for a purpose. It's the purpose which defines whether the model is reasonable or not reasonable. Okay? So this is very, very important point. Depending on the purpose, your models can change. Okay? If you are doing some, you have to do some analysis for some purpose, you will have one kind of a model. If you would like to do a different kind of analysis, you may have a different model. Right? So the purpose is very important. And the other thing to always keep in mind, a model is always a representation. Why is it important? A model is not the real thing. So if you do all your design analysis or whatever on the basis of a model, remember the model is not the real thing. The real thing is always more complex than the model. So there's always a chance that the predictions that you make on the basis of a model are not going to be true, or to some extent inaccurate, because a model is always a representation. So there will always be inaccuracies. There will always be things that you miss out in a model. The real thing is obviously different. So keep that in mind. It's always a representation. Okay. And the other thing is the purpose defines the model. Okay. So I'll illustrate that for you. Take a resistor that all of you are familiar with, resistor that you see in the lab, right? I can build two different models for this particular resistor. So this is a physical resistor, and one model that I built for this resistor is an element, is this simple model here, R. Okay, that's one model of the resistor. And the other model that I built is this one here. Now, why am I building this? Well, every lead that is there, every wire actually has an inductance. You can calculate the inductance. Okay, so every wire has an inductance, so I put an inductance here. And between two leads here, between here and here, there's always a capacitance. Because note that if I have, let's say, 1 volt here and 0 volt here, and through the air, I have a fringe capacitance. So I always have a capacitance. So if I take a physical resistor, the physical resistor is not this. This is a simplified representation, right? Physical resistor may be more accurately represented by a capacitance here and an inductor here and a resistor R here. So I'm showing you two different models of a resistor. A simple model here and a more complicated model here, right? And in general, obviously you are seeing that there is a trade-off between accuracy and complexity of a model here, right? If you want a more accurate model, the model is going to become more complex. In this case, in the previous case, obviously you are seeing that this is a more accurate representation of a physical resistor here. And obviously it's more complicated. I have capacitor and I have an inductor as compared to this one. So this one is simple and less accurate. This one is complex and more accurate, right? So that, let me show you example of diode that you're well familiar with. I've shown you several examples of models of a diode here. This is the simplest model of a diode here, where you think that in forward bias it's a short and in reverse bias it's an open. Then if you want a little bit more accurate model, you say, well, in the forward bias it's like a battery. Many times you say it's 0.7 volt. And in the reverse bias it's again open circuit. If you want to be more accurate, you say diode is a battery plus a resistor. And then in the reverse bias, again, you're modeling it as an open circuit. If you want to be more accurate, you say, well, diode is not like really a battery and all that. It's actually an exponential characteristics. So you model it like this here. And I've only shown you 4 models. I can add some 4, 5 other models in this also. On top of that, I can add 4, 5 more models here. So what is the point? The point is, I have several models. Each one of them is useful. And what defines the usefulness? The purpose. At some place, I may find that this model works fine. Right? So the purpose defines the model. And you can see here, as the simplicity is increasing here, the accuracy is increasing in this particular direction. This model will obviously, this one, will obviously give more accurate results than this one. Will always give, because this model, this model includes within it all the features of this particular model. Okay? So you have simplicity and accuracy. These are always a trade-off in the model. Okay? So now that raises an interesting question. How is an inaccurate model useful when accurate models are available? If I have an accurate model, why do I need an inaccurate model? What is the usefulness? Well, inaccurate means simplicity, right? So you value simplicity, right? So let's look into that. A simpler model makes analysis easier and results, this is more important, I would say, results understandable. Okay, let me show you an example here. Same resistor that you are here. I have 2 different models. This one and I have another model which is over here, right? Now let's take a simple circuit. The simple circuit that and these values are here. R could be 50K, L could be 5 nanohenries and 0.2 PF and all that. So let's suppose I have in the lab a circuit like this here. A resistor R1 and R2 and is connected to some sinusoidal source, right? And I want to understand the behavior of this particular circuit. Now, if I want to understand behavior, I have to analyze the circuit. I can analyze it 2 different ways. I can use this particular model or I could use this particular model, right? So let's do that. So I can use either this one or I could use this one here. Okay, so let's do that. If I use the first model, simple model here, my circuit looks like this, right? Very simple circuit, and I can easily write down the answer. We know that it's a voltage divider. R2 by R1 plus R2 is a voltage divider. On the other hand, if I use this more complicated model, so I get this representation of the circuit, and obviously I can't write it very quickly what this is. It will take me a lot of time to analyze this. And if you're patient and don't make errors, this is what you'll end up. Okay? This is what you end up. Because of inductance and capacitances, it's a function of omega. So this is what you end up. Now, suppose, I didn't show you this and I just showed you a circuit in a black box. And I said, this is the V2 by Vs. You think you can understand what this circuit is doing? Is it a voltage divider? It becomes very hard to understand what is the circuit doing. What is the role of, let's say, R1 or what is the role of R2? So the point that I'm trying to emphasize is when you use complex model, analysis will become difficult. And more importantly, the results that you will get will be hard to understand. Because why you have to, at the end of the day, you have to ask the question, why are you analyzing the circuit? What is the reason? And, one of the major reasons is I want to understand how the circuit is working, right? You want to understand what is the role of different elements that are there. I want to understand the circuit. The second reason is, okay, understanding by itself is not a goal. After understanding, what are you going to do with it? It's not that our interest is looking at different circuits and just understanding each one of them. I mean, that's a futile exercise, right? I understand everything, but what do I do with it? The eventual goal is what? After understanding, you would like to design. For a different application, you would like to design. You would like to modify. You would like to improve. So the ultimate goal is to design for different applications, right? So there are two goals that you have to keep in mind. One is that I would like to understand a given circuit, how it works. And the other one is, after understanding, I should be able to modify the circuit, improve upon it, design the circuit. These are two goals. Keep that in mind. So what I'm showing you is, I have a complex model and my analysis is becoming difficult, but more importantly, it's making me difficult to understand how the circuit is behaving. What are the roles of different elements that are there? Okay, so that's, if you want to understand what the circuit is doing, this is a much better result. It tells me that it's a voltage divider. It tells me what is the impact of R2. It tells me what is the impact of R1 in a more clear manner rather than this particular one. Okay, so that's one important point. More complicated models you will see are often nonlinear in nature. All our semiconductor devices are nonlinear in nature. Okay, and one of the things that makes the model difficult or complicated is because of the nonlinearity. Look at this example here. A diode's more accurate model is this one here. ID equal to IS, and you can see the nonlinearity, exponent VD by NVT. It's a nonlinear model here. And if I try to analyze this particular circuit, very simple circuit, using this particular model here, I end up getting an equation like this, right? And now the issue arises, how do I find I? How do I find I? It's a nonlinear equation, so what do? Well, you have to go to an iterative solution, right? Newton-Raphson method or something of that kind. You have to go to an iterative solution to solve it. So that's making analysis difficult. Okay, so keep in mind is the nonlinearity often in a device model, which is making it complex and which is making it difficult to understand. All right, the other point that I was trying to tell you is a simpler analytical result is essential for carrying out design. Okay, let me illustrate that. So we said that this is the circuit. Let's say I want to now design. Now in design is sort of is an inverse problem. In design, I'm given that I want V2 by Vs equal to 0.2 at let's say 1 kilohertz. And what I have to do is find R1 and R2. Very simple design problem. This is the circuit. Somebody says, I'm interested in V2 by Vs. He's going to apply a 1 kilohertz sinusoid. Interested in V2 by Vs equal to 0.2 and says, find suitable values of R1 and R2. Okay. So if I use a simple model, simple representation is nothing but R1, R2. It's a voltage divider. R2 by R1 plus R2 is 0.2. From there we get R1 by R2 equal to 4. And, we can choose R2 equal to 1K, R1 equal to 4K, and my design is complete. Right? So design is very easy to do. Now, suppose I use a more complicated model. Try doing the design with this one. So we have analyzed this equation. This is the, analyze the circuit. This is the equation that we obtained. Now, what I'm given is the left-hand side, V2 by Vs. And I have to find out the elements on the right-hand side. So design becomes much more difficult. Right? So when the equation is complex, remember, once you analyze, finding out V2 by Vs is easy. Just go ahead and put R2, L1, L2, L2 and all that and you'll get the answer easily, V2 by Vs. But in design, you have to do the inverse. You have to invert the equation. And as the equation becomes complicated, inverting an equation becomes difficult. Right? Finding out, given V2 by Vs, what is the right value of R2 becomes difficult. As the equation becomes difficult here. Okay? So what you're finding is that if I use a complicated model, my equations become complex. Of course, they're difficult to understand and all of that. Then the trouble becomes is that I cannot invert these equations to do the design. Design almost becomes impossible. With the simple model, I can very easily get the design. But with this one, my design becomes very difficult. I can't even begin to do the design. And as I build more complicated models, with bipolar and MOSFET and all that, the equations become so complex that you will simply, the left-hand side is given, the right-hand side will become virtually impossible for you to invert those equations. So that's becoming an issue here. So this raises an interesting problem. A simpler model allows design to be carried out, right? With a simple model, we can do the design. But simplicity means what? Inaccurate model. So my design would be inaccurate. Correct? Let me show you, illustrate to you with another example here. So this is a diode circuit. Another problem, the diode circuit is given here. And the question is, this voltage is given as 1 volt. There is a diode here. And what I want is, it's sort of an arbitrary problem here. So what I'm interested in is this voltage equal to 0.15 volts. Okay. And what I'm saying is, find suitable values of R1 and R2 such that the voltage here is 0.15 volt. Okay, simple problem. What do I do? What is a simple diode model? Replace it by 0.7 volt, right? So I do that. I replace the diode by 0.7 volt. It's a very simple model. I write down this equation. V0 equal to 1 minus 0.7 R1 by R2 plus into R1 equal to 0.15. I solve it. It gives me R1 equal to R2. That's my design. And then all of you know a very nice typical value of resistor is commonly available is 1K. So I use 1K here. I use 1K. I put it here. Then I make the circuit. I'm very happy. I go to the lab. I make the circuit. My design is complete. And I get 0.237 volt. I didn't get 0.15 volt. And why? What is the reason? Where is the error? What is the source of error that you can see? The model. I've used a very simple model of a diode, 0.7 volt. And that has made my design. So I'm saying simple model is needed for design, right? But simplicity has given me a wrong design. So what do I do? All right. Now you may say, well, let's replace the diode by an exponential diode model. More accurate, right? And then attempt to do the design. You'll find it becomes very difficult. Now this is only one diode. Suppose I had made a circuit with 4 or 5 diodes. Each one is an exponential model. Your design is going to become complicated and you will not be able to do it. Okay. So the problem that is occurring is that this is the dilemma that we have. A complex but accurate model yields results which are hard to understand and they are difficult to invert to carry out design. A simple model yields easy to understand results which can be used readily for design, but design has inaccuracies. So what do I do? If I use a simple model, I get an inaccurate design. If I use a complicated model, I don't get any design. Right? So what do I do? You may say, well, make a moderately difficult, moderately complex model somewhere in between. Well, that will be neither easy to understand and it will give me, the compromise will not work very well. Neither easy to understand nor a very, accurate result. All right. So what do I do? Which? Error analysis. Okay. So this is a problem that, what would happen is, let's say I use a simple model to design. Okay. Let's go back and see how I can tackle this. Suppose I use a simple model to design here, right? There's a simple model and I use it to design. And after design, I go to the lab, I breadboard. And I breadboard and I see 0.237. Okay, I've used a simple model, it's inaccurate, and I get a wrong value. Now, it's 0.237. But note the equation that you have here. You understand how the circuit is behaving, right? You want 0.15. What will you do? What will you do? 0.15, you want to raise this particular value here, right? Or decrease this value from 0.237 to 0.15. What will you do? Maybe make R1 less? Because now a simple model has allowed you to understand. So you know how to tinker with the circuit, how to, tune the circuit. So maybe you'll increase R2 or you'll decrease R1, right? And you decrease R1 by a certain amount and check again, right? You check again and you find from 0.237 it has come to 0.25. So you know that you have to decrease even more. So you decrease, maybe you'll go to, instead of 0.15, you end up getting 0.1. What are you doing? You're iterating, right? you're doing sort of trial and error. You understand the circuit, you know which component to touch, which component to alter, and you're doing a trial and error. And you're doing a trial and error, and you end up getting eventually the value that you want. What is the problem with this approach? The problem with this approach is, it's very time consuming. It's very time consuming. And a greater problem with this is, suppose I had 4 diodes. Now, one element, simply changing one element is not going to do your job. You have 4 or 5 elements that you may have to simultaneously work with. Right? And remember, each time you change a component, R1, R2, R3, you have to go to the lab, pick out those R1, R2, read red, green, blue, or whatever, read the value of the resistor, put it there, measure again. Imagine the kind of time, it's very time consuming. The whole exercise is very time consuming. Not only that, things get a lot worse. If you adopt this particular approach, normally circuits are not made on breadboard. If you're talking about, for example, I was mentioning ICs. So you do a design and then you send it to somewhere in Taiwan. There is a foundry which will make the IC for you, right? So your design is based on inaccurate model. You send it to Taiwan and they make the IC for you. It costs you several lakhs of rupees. It comes back after a few months and you test and you find, well, it's not working. Let me iterate, right? Let me iterate now. Let me change this component or that component, and you send it back again. It's not going to work, right? Too time consuming and too expensive. It's not going to work, right? So this iteration that I'm talking about, it can work with you on a simple basis like this. It's not going to work, for complicated and realistic cases. So what do we do? The solution is the following, which all of you know. But so what you do is, I'm just reminding you. So what you do is you do the design, but what do you do the design with? Simple model. You do the design with simple model because remember, I can't do the design with complicated model. It's not possible. The equations are too complex. Okay. So simple, you start the design with a simple model and the design is going to be inaccurate, right? So then what do? I simulate. I use a computer to simulate my circuit. And simulation is also what? Simulation is also solving equations. So, what does a computer do in a computer simulation? Again, you transform the circuit into a mathematical equations and you solve it. Except that a computer is doing it. But because a computer is doing it, I can use very accurate and complex model. I can use the best possible models that I have, let's say, and use it to simulate my circuit. Right? So this is, we simulated, and obviously my result is not going to be the same because I've used a simple model to design and I'm using a complicated and accurate model to simulate. So the result is not going to be the match. So what I do is I iterate here. Instead of iterating between design and fabrication, which is not possible, I iterate between design and simulation. I design and simulate. And we keep on doing it, iteration, till we are happy that the results of the design match my specifications. Once that happens, then I take my design and I send it for fabrication. But remember, after I fabricate, the chances are, if these models are accurate and reasonable, the chances are that my circuit will work. But keep in mind, as I reminded you, every model is a representation. It's not the real thing. Every model is a representation. It's not a real thing. So even after doing all of this, after you implement, you may have some surprises and you may have to repeat. But the point is, as you gain more experience, you build in, all those experience into your model and make sure that once you design with this particular model, after you build it, it's going to work as intended. So that's the role of, now you see the role of a simple model and a complex model. Where is a simple model needed? Simple model is needed to understand the circuit and also to carry out the design, initial design. Where is a complicated model needed? It's needed to simulate. It's needed to simulate the circuit. And what allows you to do this iteration? The fact that you understand the circuit. When you understand the circuit, you know which parameter to touch, which to increase, which to decrease, and all of that. Okay. So this is an optimization step that you do. And that's the role of a simple model. And that's the role of a complex model. All right. So simulation is an integral part of circuit design. Okay. And although is not a formal part of this particular course, what I would suggest to all of you, go to this particular site here. There is a very nice software called MicroCap. There's a demo version of MicroCap available. The demo version has some limitations that you cannot simulate circuits with more than some 50 or 100 nodes. None of our circuits will be beyond that. 50 nodes and all that. Our circuits are relatively simple. So this is a great tool for learning. Okay, all the problems that I give you as homework or as part of the exams and all of that, any circuit that I talk about here, if you, let's say you don't understand, when I'm talking about it, let's say you miss something or you want to understand something more, you can take that particular circuit and you can simulate it under different conditions and all of that, and you can learn the circuit by yourself also. Okay, so it's a great tool, freely available, download. And in order to use this particular tool, I'll give you some tutorials, post some tutorials. So it will help you to use this particular tool to simulate the circuits here. For example, when I was showing you these, these circuits here, this circuit here and this circuit here, these have all been drawn in that particular, using that particular tool, simulator. So from time to time, I'm going to show you simulation results obtained from that particular tool. Okay. For example, all these results are from that particular tool here. So as I was showing you this particular example, that when I use R1 equal to 1K, R2 equal to 1K, I get 0.237 volts here, because my diode, I assume 0.7 volt. My diode is not 0.7, it's 0.762. Okay, and after iterating, this is what happens here. This is the correct design. I wanted 0.15 volt here. The correct design node has 20 ohms here and 20 ohms here. And the diode voltage is 0.850. So diode, we'll talk about it later. We keep on making an assumption diode voltage is 0.7. To some extent it's true for certain cases, but for many others it's not true. Right? So look at the difference. If I use the simple 0.7 model, I obtain, let's say, a 1K. The 1K is giving me an inaccurate answer. The actual suitable value of resistor is only 20 ohms. 20 ohms here and 20 ohms here. Of course, a design doesn't mean that there's a unique answer. You could get this 0.15 volt in other ways also. Okay, so often there are multiple answers to a problem. Okay, so this is a summary of our discussion regarding the model here. Obviously, any model we want it to be accurate, but often we want accuracy, but the models become complex. When we strive for accuracy, the models become complex. That makes analysis difficult. That makes insight difficult here. And also, models are not, the complex and accurate models are not very useful for carrying out the design, because the equations that we get are complicated. Simple models are obviously very easy to use, quick analysis. They help us to understand the circuit, and we can easily design with it. And the way we overcome the deficiencies of a simple model is that after design, we simulate it. We simulate it with a more accurate model and correct our design. Okay, so that's the, a brief discussion related to simple models versus complex model here. All right, how are simple models obtained? By the way, I'll keep on droning, keep on talking, unless you stop me, all right? So if you have questions, please stop me and ask for a discussion regarding any of the points that I want. Otherwise, I'll keep on moving from one topic to the other, all right? The syllabus is vast, and so if you want to stop, want to discuss something further, please stop me, okay? So how are simple models obtained? Okay, again, keep that in mind. It's a representation for a purpose. The device is complex, right? As I said, device is nonlinear, device is complex. So how do I obtain a simpler model? One of the ways in which I do it, you will see I've drawn a graph here, and this is a typical graph of a MOSFET drain current versus the gate voltage. It looks like this here. It's drawn on a semi-log axis here. This is a log axis, and this is a linear axis here. So this is the behavior of a MOSFET. All right. Now, if I look at the equation here is sort of exponential. The equation here, if I try to look at it, is sort of square. But, it's going from exponential, somewhere here is complex. is making a transition from exponential to square. So a MOSFET is complicated, right? A MOSFET is a complicated nonlinear device. Now, how do I obtain a simple model? I obtain a simple model by narrowing the scope of the model. How do I obtain a simple model? Well, remember, if I were to write one single equation which covers the entire behavior, that equation is going to be, one single equation which captures the entire behavior. That equation is going to be complicated. You try doing it. One single equation which captures the whole thing here is going to be a complicated equation. So what I do is I narrow my focus. So I look at only this region here. And this region, when I narrow my focus and I say, narrow the voltage range, then I say, well, it's an exponential model here. If I narrow my focus here, I say, well, this is my quadratic model here. This model is simpler than the overall model of a MOSFET here. So one way in which we build simplicity is by having different models for different regions of operation. That's how we make the model simple. One model which works over the entire region of operation is complicated. It's a very complicated mathematical equation. But when we say, okay, for this region, I have this model. For this region, I have another model. For this region, I have another model. Each one of those models becomes simpler. But what is the problem that occurs? Each one of those problems becomes difficult. I end up having problems at the transition region. Now, transition region means I have neither an exponential model nor a quadratic model. And transition regions become difficult for me. So I have a nice exponential model here, a quadratic model here, but this region I don't capture. So that becomes difficult. So if you are, when you are doing your design and you are using, let's say, an exponential model, if you are somewhere here, you're fine. But if you start straying into this particular region, then a lot of errors will creep in. Okay. So when you use different models for different regions of operation, one of the things you have to be very clear is every model has a range of validity. You have to be aware of that. Every model will have a range of validity. It will be valid between this voltage range to this voltage range, or this current range to that current range. Very often we forget that. We take a model, we apply it, we get a result, and we go on without worrying about was that model valid? Okay, so keep that in mind. Every model has a range of validity because simple models are being built. How? By confining the model to small regions of operation. That's how we are doing it. Okay. Another class of models which are simple is something that you've heard, and this is something extremely important for analog circuits. Small signal model. Okay. Now, what are small signal models? We'll have a little bit more discussion related to this. It shows you an IV characteristics of some element. And small signal model, what it says is, my device here, X that you see here, whatever the device is already biased at some voltage. It's already here at some point, at some voltage. And on top of that particular voltage, if I superimpose another voltage, another small voltage, then what is the response of my device here? That's a small signal model. And the reason why we build this small signal model, you'll see, is that my device is nonlinear. And the small signal model that I built, because it is small, is linear. And I told you that you obtain simplicity often by linearizing. Linear models are simple. Nonlinear models are complicated, right? So small signal models are an outcome of linearizing a device, linearizing the mathematical equation, okay, and obtaining it. So let's discuss this in a little bit more detail. If you want to understand small signal model in detail, you have to go back and look at the concept of incremental circuit analysis. And then you'll see where how small signal models are emerging from the requirement of incremental circuit analysis. Okay, so let me take this particular circuit as an example. So a circuit is given, it's a linear circuit, right? Suppose you've already analyzed the circuit. You know what the voltages are and currents are and all of that. You've done everything. Okay, but you would like to understand after analyzing further, if I change my voltage by let's say by a certain amount, I'm not saying small. If I change the voltage by a certain amount, let's say here, what will be the change in V0? Suppose I ask that question, that if I change my voltage by a certain amount, what will be the change in V0? What am I doing? I'm doing incremental circuit analysis. Why am I calling incremental circuit analysis? Because I'm, creating an increment of a voltage or something in my circuit, and I'm asking what is the consequence of it, right? For, at various places, it would be of interest to me. If I double this, what will happen? Will this voltage double? Or if I take this resistor and reduce its value by 50%, what will happen? In all of this, what am I doing? I'm doing incremental circuit analysis. I'm saying, I'm changing the value of some component, some voltage by a certain amount, and I'm saying what is the change in some voltage, some current, some power somewhere else in the circuit. So I'm talking about incremental circuit analysis here. Okay. So as an example, suppose I say, well, say delta Vs1 is 10 millivolt. What is the effect on delta V0? Suppose I ask that question. Remember delta, look at the word, and that's where the incremental circuit analysis comes in. I'm asking for a change. Now, why would delta Vs1 10 millivolt be of interest to me? Well, this is an arbitrary circuit, but suppose this voltage is derived from a power supply. And power supplies, all of you, studied in your circuits course, they have a ripple. So I could have a 10 millivolt ripple, right? So this could be a 10 millivolt ripple. And I may be interested in knowing that if I have a 10 millivolt ripple, how much ripple appears over here. Okay. So, there are many, many places where I'm interested in that if something changes in one part of the circuit, what is the consequence on some other part of the circuit? Okay. So my interest is in changes. My interest is not in absolute values. It's in changes. That's why we are calling it incremental circuit analysis. So if I have this particular interest to do it, well, again, note that all these diagrams that you see here, they're all derived from simulators. It would take me, a lot of time to figure out all the values, calculate. So very easy to go draw the circuit and get the answers that you're looking for. Anyway, so I have this circuit. So one way of doing this particular problem is, let's say this were 1 volt initially. And then what you do is you analyze the circuit for 1 volt. Then you analyze the circuit for 1.01. And you look at the values of V0 for 2 different cases, subtract, and you know what the changes are, right? So that's what I'm doing. So I have 1 volt here, and I'm not calculating. I just simulate. It's easier. So I get minus, how much is it? 14.5. Minus 14.5 here, right? Next, what I do is I change this to 1.01, and I get minus 14.495. And what is the effect of changing this by 10 millivolt? I subtract these two and I get an answer which is 5 millivolt. Right? The method will work. What is the problem? What problems do you see? Well, I have to do 2 times analysis and all that, right? I have to do an analysis here, then I have to do an analysis here. I have to subtract and get it. That's one part. What is the other problem? Note here, how accurately do I have to do the analysis? To the 3rd decimal place. Right? 0.495. I have to do it to the 3rd decimal place. Right? So I have to keep track of all the decimals. And if I do it to the 1st decimal or the 2nd decimal, it's going to create a problem for me. So I have to do very accurate analysis to get the right answer here. 5 millivolt. Okay, that's the problem. As the circuits become more and more complex, at various places, we round up, we make approximations. That's how we get an answer. Otherwise, getting an answer becomes difficult. So at various places, in bipolar transistors or in a MOSFET, there are various places we make various approximations. And this tells you that I have to do very accurate analysis to get the right answer. I have to do it to the 3rd decimal place. Well, how would you solve that particular problem? Suppose I didn't want to do this. First do it with this one and then analyze with 1.01, then subtract and then do it. Well, there's a simpler way. Use superposition theorem. Right? Superposition theorem. What am I saying? I'm changing Vs1 by a small amount. So let's put this source here. Now, what am I interested in? What is the effect of delta Vs1 on V0? So what do? I use superposition theorem. I remove all the other sources. Right? So that's a simpler method. Why do like that brute force approach? So when I remove all of the sources, I'm going to remove Vs1 and I'm going to remove Vs2 and I'm going to remove Is. Removing a voltage source means shorting it. Removing a current source means opening it. And so my circuit becomes here. And then I simply, now note, this circuit is only for delta Vs1. And therefore, the output is also delta V0. Because it is telling me what is the change in V0 due to Vs1. Alright. So I calculate and I get an answer very easily. I don't have to do very, very accurate to the 3rd decimal place. I don't have to do that. This is 10 millivolt and analysis becomes much easier. So superposition is helping me to figure out that if something changes in one part of my circuit, what will be the consequence on another part of the circuit. Superposition is helping me, which is very nice. But except that, what if I had a diode or a transistor? Will superposition work? No. Why? Because superposition requires the circuit to be linear. Then what do I do? If I have a diode or a transistor or other nonlinear elements, then I'm stuck. I can't use this very nice method. It will not work. So let me talk about superposition from a different angle here. Something similar will happen, but from a different angle here. So I have this circuit that you see, okay? And let's transform this circuit into equations. So I have Vs1 equal to I1 R1 plus V0, I1 equal to, we write a KVL and we write a KCL at this particular point and we get these two equations, okay, for this circuit. Now I'm saying, let me change Vs1 by a small amount. And as I change Vs1 by okay, small is not the word. Let me change Vs1 by a certain amount. Now as Vs1 changes, you realize that in principle, everything else will change. I1 will change by some amount. V0 will change by a certain amount, right? So let's do that. So what I'm doing is, I'm changing Vs1 by a small amount. This is small Vs that I've written. That's the increment in Vs. So Vs1 changes by that amount. Current I1 will change by a certain amount. Voltage V0 will change by a certain amount. The small letters show you the changes, the increments, okay? Current I1 will change by some amount. And similarly, Is, of course, is a constant, doesn't change. And V0 will also change by a certain amount. And so we write these equations. As a result of a change in Vs1, everything else that can change will change in principle. So now what do? We subtract 1 and 2 from 3 and 4. Suppose I subtract it. What do I get? If I subtract, I end up getting these equations here. You can do that. You end up getting Vs1, this change, equal to I1 R1 plus I1 R2. I get this change here. As I subtract 1 from 3 and 2 from 4, I end up getting these equations here. And now Vs1 equal to I1 R1 plus I1 R2. So very easy to solve. I get the answer that I'm looking for. Okay. But not only that, look that this equation, what does it represent? I told you that you can have a circuit and transform it into an equation. You can have an equation and transform it into a circuit also. So this is equation that you see here is nothing but this circuit. And what is this circuit? We call it as an incremental equivalent circuit. Why? Because the circuit deals with incremental values. It deals with incremental change here. It deals with incremental change in V0. It deals with incremental change in I1. It deals only with incremental values, not the absolute values, incremental values. How do I obtain this particular circuit? I obtain this particular circuit. I've shown you this particular method, and you realize that I obtain this circuit, let me generalize and say, by building incremental model for every element. Every element in the circuit that you have, if you build an incremental model, you get an incremental equivalent circuit. And that circuit can give you answers to that if you change something in one part of the circuit, what will happen in another part of the circuit. Okay. So incremental circuit analysis can be done through an incremental device model, an incremental circuit model. How do you obtain incremental circuit model? By building incremental model of every element in the circuit. Incremental model of every element in the circuit. Okay. So we'll stop here and we'll continue from this point. Okay.